Hello everyone, this is Shudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. Today I'm going to talk about a topic of electrical circuit and network. Electrical circuit and network is one of the most important subject of electrical engineers. So please solve or learn this subject from the beginning so that you can solve different types of problem. You can solve different types of circuit analysis problem using this concept of this subject. Now the lesson plan is here. So in this lesson plan we have total 3 units to cover. So within that, the first one is single phase AC circuit and resonance. So today it's 2.3, and then in unit 3, unit 4, unit 3 it's principle of circuit analysis, AC and DC circuit, and then unit 5 networks theory, statement procedure, areas of application and limitations. So today's subject I'm going to talk or discuss about parallel AC RL circuit. So here today's topic of discussion is parallel RL circuit. Now first we have to understand that what is this parallel RL circuit. In parallel RL circuit, resistance, resistor, inductor are connected in parallel. So in series RL circuit, resistor and inductor were connected in series. That means this was the resistor, this was the inductor that was connected in series for series RL circuit, but for this case the resistor and the inductor will be connected parallel. This is the basic difference between the series and the parallel connection. With each other, and this combination is supplied by voltage source Vi. That means there will be a voltage source. The voltage source will be Vi, input voltage source. The output voltage of the circuit is V out. So one source voltage, input voltage, one the output voltage will be there, and inside the circuit there will be a resistor and inductor which will be connected in parallel. So minimum this is the requirement to become a circuit, or you can say a circuit, a parallel RL circuit. Since the resistor and inductor are connected in parallel, the input voltage is equal to the output voltage, because we know that the voltage source always connected parallelly with the circuit. So in the left side, in the receiving end and the sending end, in the both side, the resistor and inductor parallelly connected. So we can easily say, using the concept of voltage source connected parallelly through with the circuit, we can easily conclude that the input voltage is equal to the output voltage. But current flowing in the resistor, so voltage is same. For this case, the input voltage is equal to the output voltage. So V in equals to V out. Why? Because so the question it is written that the resistor, the inductor will be connected in series, and if it is V in and it is V out, so all are connected parallelly in this circuit. So Vn equals to V out. But the current is not same. The current flowing in the resistor and inductor are different for this case. Current flow will be different because some current will generate and this is the current. So from this part the current will flow, and from here the current will change. Some current will flow through this path, some current will flow through this path, obvious, and from here the current will come, it will oppose here, it will go from here. So the value of the current of the terminal will be different, but the voltage of the both side of the terminal is same. That means the current through the resistor and inductor will be different. So this is the few points you have to remember for a series parallel RL circuit. Now the circuit which we already discussed in our previous slide, we already talked about the circuit. So that is written here, V input, and here it is V output, both are same because the resistor and inductor connected parallelly. Fine. So the voltage VIN and VOUT, V input and output are same, but the current is different because the current which will flow through this resistance, they consider the current is IR, and the current which is flowing through the inductor, that is IR. This current value is different. So let us say IT is the total current flowing from voltage source in amperes. IR, the current flowing in the resistor branch in ampere. So IR current is flowing through the resistor, this current, no problem with this. And then IL, the current flowing in the inductor branch in ampere. IL is also flowing through the inductor branch in ampere, and theta, the angle between IR and IT. So here we draw the same figure where this is our IR, this current, this is IL, the current which is flowing through the inductor, and we know that for inductive circuit, current always lags behind the resistive voltage. The current always lags behind the voltage, and resistive current and voltage and the resistance lie in the same phase. So if we consider IR as reference, so IL will lag behind the voltage. So this IR is the current which is flowing through x-axis, and IL will be the current which will flow through negative y-axis. Now IT is the total current, IR is the current flowing in the resistor branch in ampere. Yes, resistor branch. IL is the current flowing in the inductor branch in ampere. No problem with this. Theta is the angle between IR and IT. So how to find the total current? The total current is the vector summation of IR and IL, that is IT. We consider as IT. So the current IT square, so using the Pythagoras, IT square will be equals to IR square plus IL square, because this is our IL. Okay, so if it is IT, you can easily say that that is equals to IT square equals to IR square plus IL. Fine. So in this way we can find the current. Now here in the complex form the currents are written as, we have to understand that what will be the current in the complex form. So we already know that IR equals to V input by R. So it is V input by R. Fine. IL equals to V in divided by J omega L, where omega equals to 2 pi F. So IL is equals to minus J V in by omega L, because where 1 by J equals to minus J. How it is 1 by equals to minus J? So here it is written that IL equals to V in divided by J omega L, where omega equals to 2 pi F, phi equals to 3.14, or you can say 22 by 7, and F equals to 50 hertz. Consider. L is the value of the inductor. V input is the voltage, supply voltage. Now, what is J? Is the complex value, that is minus 1. So, if we multiply the numerator and denominator by J, then what will happen? Here, J into J into omega L, J V in. So J into J, because J equals to root over minus 1. J into J means root over minus 1 into root over minus 1. That is equals to minus 1, because square and root will vanish. So it will be minus of JV in divided by omega. So that is written here. IL equals to minus JVN by V in by omega L, where 1 by J equals to minus J. Therefore, the total current IT will be equals to V input divided by R minus J V in input by omega L. So the total current, we know that the total current is IT, and what is IT? IT is V divided by Z. Okay, so IT is equals to V by Z, and here Z equals to R minus J V in by J omega L. So in this way, we can find the value of the total current of the circuit. Now, here we already calculate the values. So here in the circuit we have a resistance, we have inductor. That means the resistor and inductor is here, and with the Z we represent total impedance of the circuit, obviously in ohms, because ohm is the unit of the impedance. Then R equals to resistance of circuit in ohms. You all know that R equals to resistance and the unit is ohms. Z is the impedance, the unit is ohms. And L is the inductor of the circuit and the unit of L is the Henry. And the last one is XL. XL is the inductive reactance in ohms. So XL is inductive reactance. If it is XC for RC circuit, capacitive reactance. Okay. So L is the inductor of circuit in Henry, because the unit of the inductor is Henry, represented with L. Resistor is represented capital R, and impedance by Z, and XL is the inductive reactance. So this is the circuit where a AC supply, AC voltage source is connected. With that, a resistor and inductor is also parallelly connected. So this type of circuit we can say it's a parallel RL circuit. Now here, since resistance or resistor and inductor are connected parallelly, the total impedance of the circuit is given by. So how can we find the total impedance of the circuit? Because these two are connected parallelly, R and JXL. So when something is connected parallelly, we know that suppose this is the basic parallel connection. If it is R1, if it is R, then if the equivalent is Req, so the formula is 1 by Req equals to 1 by R1 plus 1 by R2. So the same concept, 1 by Z, we consider Z is the total impedance, that is 1 by R for resistance and 1 by JXL for inductance. So 1 by Z equals to 1 by R plus 1 by JXL. So we know that this is equals to R1 R2 divided by R1 plus R2. So for this case also, that is equals to, we can say, R into JXL, okay, divided by R plus JXL. Look, this is written here. R into JXL divided by R plus JXL. So same concept of the resistor here we are applying. Since the resistance and inductance, or resistor and inductor, are connected parallelly, the total impedance of the circuit Z will be equals to R into JXL divided by R plus JXL. So with this method, or the help of this simple method, we can find the impedance of the circuit. Now, in order to remove J from the denominator, so always we have to remove the denominator from the equation. So this is one of the calculative or calculation that we always need to remove the complex number from denominator as per the rule of the complex number. In order to remove J from the denominator, multiply and divide numerator and denominator by R minus JX. So up to this, I think no problem with anyone. This part is already we calculate from the previous figure. So previous calculation, impedance calculation. So how can we remove the J from the denominator, from this part? How can we remove this? We have to understand that from this part we have to remove this J. How can we remove this? We need to multiply R minus JXL in both in denominator and numerator. So if we multiply this one with this, so it's a calculation that R square, yes, R square XL into J minus J square R square XL square. So simple multiplication, and here it will be R square plus XL square. Why it is R square plus XL square in the denominator? Because R plus JXL into R minus JXL. Okay, so the formula of the algebra, A plus B into A minus B. Tell me what is the result? A square minus B square. So here also we can apply the same problem, same formula. So first one will be R square. Now a minus is there, minus will come, no problem. Just take minus J XL whole square, no problem. Same formula, this one, and we just apply the same algebraic formula. So this is R square minus J square into XL square. So XL square, we don't have any problem with XL square. But the question is, what is this J square? J equals to root over minus 1. So J square equals to minus 1, because this root J square, root over minus 1 into minus 1. So root will vanish. So only minus 1 will be there. And so minus 1 into XL square. So R square plus XL square. So in this way, we can find this value, since J square equals to minus 1. So finally, we separate the Z in real part and imaginary part. Look here. In the real part, we'll find R XL square divided by R square plus XL square. And in the imaginary part, it is plus J R square XL R square plus XL square. Now, if you think in parallel RL circuit, the values of resistance, inductance, frequency, and voltage supply voltage are known for finding the other parameters of RL parallel circuit. Follow this step. What is this? In parallel RL circuit, the values of resistance, inductance, frequency, and supply voltage are known for finding the other parameters. Okay, parallel circuit, follow these steps. So what is that step? The first one, step 1. In step 1, follow in step 1. Since the value of frequency is already known, we can easily find the value of inductive reactance. Try to understand very carefully. Since the value of the frequency is already known, 50 Hz, we can easily find the value of the inductive reactance. Now the question is, what is inductive reactance? That is XL. And we know that inductive means L, reactance means X, so XL. So we can find the value of this XL, that is 2 pi F into L. If is the frequency, L value will be given, so you can easily find this XL. So that is step 1. Now step 2. What is step 2? Step 2 is, we know that in parallel circuit, the voltage across inductor and resistor remains the same. So in parallel circuit, we already talked about this topic, that the voltage across the voltage across the inductor and the resistor remains the same. So VR equals to VL equals to V. Supply voltage, the input voltage, output voltage, the resistor and the inductor all are connected parallelly. And we know that if voltage source always connected parallelly, so for that reason, like this is the voltage source, resistor and inductor. So for that reason, if the voltage drop across the resistor VL, the voltage drop across the inductor VL, so all are same. So for that reason, it is written VR equals to VL equals to V. Now on step 3, use Ohm's law to find the current flowing through inductor and resistor. Use Ohm's law to find the current flowing through the inductor and resistor. So we have to use only simple Ohm's law, and we all know that what is Ohm's law, V equals to IR. So using the Ohm's law, we can find the current flowing through the inductor and resistor. So current flowing through the inductor, that is XL. If we consider the current is IL, then it is simple using Ohm's law. I equals to V by R. So IL equals to V by XL. And for resistor, the current is IR, so it is V by R. So in this way, we can easily find the value of current across the resistor and the inductor. Step 3. Now in step 4, now calculate the total current. We already calculate the total current from the previous slide, that the angle between the resistive current and the inductive current is 90 degree. So the vector, using the vector triangular formula, we can easily find that the total current, if it is IT, so IT square equals to IR square plus IL square. This is the method. Find the total current. Now, step 5. What is step 5? Determine the phase angle for resistor and inductor. And for parallel circuit, it's always phi r equals to 0 degree and phi l equals to minus 90 degree. Phase angle for resistor and inductor for parallel circuit. Phase angle for resistor, it is phi r, is obviously 0 degree, because the for resistor the current and the voltage angle is always in the same phase, and for inductor the current and voltage, the current is always lags 90 degree, lags behind 90 degree from the voltage, so that it is the phase angle of the inductor phi l equals to minus 90 degree. Now step 6, what is step 6? In step 6, since we have already calculated the total current flow in the circuit, there is IT, and voltage V, and we know that supply voltage is V, also known to us by Ohm's law. So we can easily calculate the total impedance. So what will be the total impedance? Z equals to, simple, this is Ohm's law, only Ohm's law, using Ohm's law we can solve different types of problem. So Z equals to V equals to IR. You know what is Ohm's law? V equals to IR. For this case, V will be equals to R is Z here, impedance, and I is IT here. So we have to find the impedance. So Z will be equals to V divided by IT. Okay. So this is the process to find the value of the impedance. Now we are moving to the next slide, that is step 7. Now calculate the total phase angle for the circuit which is given. So total phase angle, if we consider the phase angle is phi t, that equals to tan inverse IL by IR, because IL is the length and IL is the base x, and along Y it is IL. So the total phase angle, this is the total phase angle for the circuit, phi equals to tan inverse IL by IR. So what is the conclusion? The conclusion is the total phase angle of a parallel RL circuit. Look here carefully, the total phase angle of a parallel RL circuit. Each one parallel RL circuit always lies between 0 to minus 90 degree. Yes, we already talked about this. So the total phase angle of parallel RL circuit always lies between 0 to minus 90 degree. It is 0 for pure resistive circuit and minus 90 degree for pure inductive circuit. It is 0 for pure resistive circuit and minus 90 degree for pure inductive circuit. Because inductive circuit, we know that current always lags behind voltage 90 degree, and for purely resistive circuit, the voltage and current always lie in the same phase. For that it is 0, and for inductive circuit the current lags 90 degree. For that it is minus 90 degree. So that is the topics today I just cover for your better understanding. You can go through different books, practice from the books, practice different types of problem from the books, different exercises, different example from the books. That will be helpful for you to develop your knowledge more and more. For any doubt, any confusion, you can contact with me anytime. That will be helpful for you also. I will be available there for your mm, help. So my request, please follow the books, and if possible, just repeat this lecture, listen this lecture repeatedly, so that your concept, if any doubt is there, it will be clear. Thank you all. Thank you for your patience. Thank you for watching the lecture. Goodbye. Take care.